Today we'll talk about Bayesian classifier, and hopefully after that we'll be able to talk about Fisher's linear discriminant function. Okay, so what does it say? These slides describe two classifiers, as I said, Bayesian and Fisher's linear discriminant function. The Bayesian is a simple classifier that is fast and easy to train. It's very popular for text classification tasks. FLD, which stands for Fisher's linear discriminant function, is also a linear classifier, and it can also be used for dimensionality reduction. So we will start with these two. And remember, last time the classifier we talked about was K nearest neighbor classifier. That is not a linear classifier, if you remember correctly. The boundary that we saw in two-dimensional space for the example that we looked at, that was a highly complex nonlinear boundary. All right. So what is the Bayesian classifier and what does it depend on? Let's see. Right here. Okay. So it's a Bayes classifier which uses the probabilistic framework for solving classification problems. And it is based upon the Bayesian formula that we looked at earlier when we talked about basic introduction to probability and statistics. All right. It's an example of generative approach. You remember I mentioned that there are three kinds of approaches people use for designing classifiers. One of them is the generative approach, which looks into the probability distribution of the data and tries to build a classifier using that information. All right. So if you look at the Bayes theorem, which basically relates what you are observing, what the a priori probabilities are, and based upon your observations and a priori probabilities, what is the posteriori probability. That's what the Bayes formula does. It links those quantities. All right. So let's look at this Bayes formula that is shown here. So basically, we are saying here on the left-hand side, knowing that event B has taken place, or given that we know about B, what is the probability of A? And that probability is given by the formula that you have on the right-hand side. And if you look at the first term on the right-hand side in the numerator, it is basically probability of B given A has happened, or knowing about A, what is the probability of B. All right. Next one is multiplied with probability of A. And the whole thing is divided by probability of B. Okay, so that's the formula for Bayes' theorem. And the different terms in this theorem have different terms. They are known by different things. For example, on the left-hand side, the probability of A that B has taken place is called posteriori probability, or simply posterior. Probability of B that A has happened is called likelihood. Probability of A is the a priori probability that A is going to happen. And probability of B also is the a priori probability. And in this case, it is also known as the evidence. So basically what the Bayes theorem does is that it relates conditional probability with evidence and priors. So let's look at what is the scenario we assume when we talk about using or designing Bayesian classifier. So we will assume that we have D features. D is the dimensionality of our feature space. So we have D features. We can represent them using x1, x2, all the way up to xd. And to keep discussion simple, we will assume that we have two classes. We will label them as class C1 and class C2. So what we have done is we have a collection of objects that come from either class C1 or from class C2. And on each of these objects, we have made D measurements. So basically, we have a collection of vectors in D dimensions, and these vectors come from two classes, C1 or C2. All right. So if we want to make use of Bayes' theorem, then according to the Bayes' theorem, the probability that a given observation vector x belongs to class C of j is given by the Bayes formula that is shown here. All right. This formula is no different from the formula that I showed you in the previous slide, except that there I had used A and B. So instead of A and B, now we have, observations are vector x and classes are C of j, where j could be 1 or 2. All right. So basically what we are doing is, given an observation vector x, knowing what are the a priori probabilities of class 1 and class 2, and knowing how x is distributed, we can apply the Bayes formula to calculate the posteriori probability for class 1 and class 2. All right. So basically, the formula allows you to calculate two numbers. Those are the two posteriori probabilities. And if you have to make a decision, obviously your decision is going to be in favor of C1 if the posteriori probability for C1 is more than the posteriori probability for C2. And if C2 has a higher posteriori probability compared to C1, then you are going to go with C2. All right. So that is basically what the simple Bayesian rule is. All right. So we classify vector x as belonging to class C1 if the posteriori probability, which is the result of this calculation, is better than the posteriori probability for class 2. All right. Now, it might happen that both the probabilities come out to be same. In that case, basically, we have a tie situation, and all you can do is go either with class 1 or class 2 in any random fashion. So randomly, you can pick either class 1 or class 2. All right, so that's really how the Bayes classifier works. Now, why we call it naive Bayesian? Because in the previous slide, I called it Bayes classifier. All right, in this slide, I'm calling it naive Bayesian. All right. The reason we call it naive Bayesian is that when you look at the distribution, probability distribution of x, and you want to characterize that distribution by the probability density function. All right. Normally, the observations or the components of this feature vector x, they will show some correlation. In most situations, there is certain amount of correlation. All right. But in naive Bayesian, what we do is we make an assumption that these features are not correlated. That is, these d values that represent a particular object, those d measurements are independent of each other, which is really not true. But what happens is that if we make that assumption, life becomes a little easier. And the resulting degradation in the performance is not that much. That means you can make an assumption and live with that assumption without paying too much penalty for that. All right. So that's why we call it a naive Bayesian, because we assume the features are independent. Now, just to get an idea of what advantage we get by making this independent assumption, let's take a situation where each feature is a binary feature, not a continuous feature, but a binary feature. All right. And let us assume that we have 10 features. All right. So if you have 10 features, then the total number of different possibilities for vector x, that number is 2 to the power 10. All right, because each feature is independent, it's a binary, so 2 to the power 10 possibilities are. All right. So if you do not make an assumption that these features are independent, then what you will need to do is you will need to collect many more examples than 10,024 examples. So you will collect about 100,000 or 200,000 or 500,000 examples. And based on those examples, you will calculate the probability for every combination for x. And you will then use those numbers to plug into your Bayesian formula. On the other hand, when you make an assumption that these features are independent, then all you need to do is to calculate 10 probabilities for class 1 and 10 probabilities for class 2 for each of those features. So basically, you are coming down from so many probability calculations to such a smaller number. And obviously, when you have to calculate 10 probabilities for class C1, the number of examples you need, if you have 1,000 examples or 500 examples, that's good enough, reasonably good enough to do that calculation. All right. So by making this assumption, you are able to do two things. Number one, you are able to reduce the requirement on your number of training examples that you want to have. And number two, you are able to work with fewer conditional probabilities than you will be working otherwise. All right. So that's the basic reason. And if you look at this formula, you will see that in the numerator on the right hand side, we have probability of class Cj multiplied with that pi sign stands for multiplication operation. So basically, you are multiplying 10 conditional probabilities. What is the conditional probability for for first component of feature vector being equal to 1, given that it is coming from class 1, or given that it is coming from class 2. All right. So basically, you take the product of these 10 conditional probabilities into calculation, and that product symbol is basically the pi symbol. All right. So that's basically your naive Bayesian classifier. All right. So one can write down the formula that you want to assign a given observation vector x to class C1 if that if you go back to the previous slide and just a minute, let me go back. Okay. Now, if you look at this formula here, look at the right hand side and look at the denominator. You will find that the denominator has nothing to do with whether j is equal to 1 or j is equal to 2. All right. So what one can do is one can forget about the denominator, because our interest in classification is just to see which posteriori probability is higher. Okay. And since this denominator is common to both the calculations, so even if we don't take this into consideration, we are not losing anything. All right. So that's why in practice, the naive Bayesian classifier rule is specified as shown in this slide. That is, you basically assign X to class 1 if the posteriori probability for class 1 given by this formula turns out to be more than the posteriori probability for class 2. All right. So that's really, there is all about the naive Bayesian, except that now question is, how do we expand this to C classes when we have more than 2 classes? And also, how do we get hold of these probability? All right. So if you have more than 2 classes, so say you have C classes, basically the rule remains the same. That is, instead of calculating 2 posteriori probabilities, now you will calculate C posteriori probability. And again, you will go in the favor of class for which the posteriori probability is going to be highest. All right. So one can write that formula as shown in this particular slide. And again, in case of a tie, you basically make a random selection. All right. So that's how this works. So now let's look at an example of naive Bayesian classification, just to get a better understanding of what we're doing. So let's say there is a company like Netflix, and this company divides its customers into 2 categories. Either a customer has a conservative leaning or customer has a liberal leaning. All right. So those are 2 political leanings or viewpoints. So it says, all right, this customer is conservative, this customer is liberal. All right. And it turns out that 90% of its customers are conservative. What the company does is that the company uses this classification of customers to serve the appropriate ads to maximize its revenue. So basically, if the customer is a conservative customer, you want to show them the ads that will run on Fox News channel. That's a conservative channel. All right. On the other hand, if the customer is a liberal customer, then basically the ads that he or she might see are similar to the ads you might see on MSNBC, which is a liberal channel. All right. So basically, based on what the customer's classification is, they decide which ads to show on that particular scale. All right. And this is all done nowadays through streaming and all that. So not a big deal. All right. And the company has collected data through the habits of customers, as well as through its programs that it runs. So basically, it has 4 shows or show category, 4 categories of shows: S1, S2, S3, S4. And basically, it has got this data that customers that are classified as liberals, 95% of them like shows in the category S1. And for the remaining 3 categories, the percentages are as shown. Similarly, for conservative customers, they have a different set of percentages. Their show likings are obviously different. So those numbers are shown. All right. So that's what the information company has. All right. Now, a new customer signs up, and the company finds that this new customer likes S1 and S3. It shows that are from category S1 and S3, they are alike. And he or she dislikes S2 and S4 show categories. Assuming that the likes and dislikes of different shows or show categories are independent of each other, how should the company classify this new customer? Should this customer be classified as a liberal, or the company should classify this customer as a conservative? And based on the classification, then company will run some ads and things like that. All right. So this is the kind of problem which is easy to solve with naive Bayesian classifier. All right. So let's see how we will do it. So let's look at the a priori probability. All right. If you pick a random customer from this company, what is the probability that that customer is going to be a conservative customer? That probability is 0.9 because 90% of the customers are conservative. All right. So the a priori probability, before we know what shows this particular customer likes or does not like, we know that there is a 90% chance this person will be a conservative customer, or there is a 10% chance that this person is a liberal customer. All right, so we have those numbers. Now, yes, please. These are based on the historical records of the company. Okay, if whichever problems you work, there is always historical data or some other data to give you an idea of, of what those a priori probabilities. For example, if you are looking at classification of letters or vowel sounds, if you just look at the English letter, for example, the letters that are characterized as vowels, they have a much higher frequency, and the letters that are characterized as consonants, they have a different frequency. And in fact, there are tables available that tell you what exactly is the probability of letter A in any English text. Okay. So those numbers are based on, some historical records or whatever information they might have. All right. So basically, and of course, for the liking or disliking, basically that's through the surveys. You conduct some surveys or people provide some feedback, then you can collect that information. All right. So if we look at the second bullet, first term, all right, we are showing what is the probability of S1 being equal to 1, means S1 being liked, all right, given the customer is a conservative customer. All right. So that data we already have, because if you look at my previous slide, we have that percentages. All right. So we have that. Similarly, what is the probability that S2 will be liked, the shows of type S2 will be liked by conservative customers? That probability is 0.82. And similarly, all the other probabilities are there. All right. So basically, if you look at the problem, we have the a priori probability, we have all the conditional probability. Then what we can do is we can plug in all these numbers in our Bayes formula and calculate what is the probability of this new customer being a conservative customer or being a liberal customer. So that is what we will do in the next slide. So the new customer likes S1 and S3, but does not like S2 and S4. All right. So with that information, we can calculate the posteriori probabilities for both the cases, whether the customer is going to be a liberal customer or a conservative customer. All right. So we plug in all these numbers and we find that the probability that this customer is a liberal, that number turns out to be 0.0014. And if, we have two probabilities, all right? So one is 0.0014 and other one is in the third line, 0.00013219, all right? Now remember, these are the numbers that have been obtained by discarding the denominator in the Bayesian formula. All right. So that's why sometimes you might say, well, there are only two possibilities. and the two probabilities then should add up to 1. How come, they are not adding up to 1? The reason they are not adding up to 1 is because we discarded the denominator part. All right. So if we don't do that, or if we normalize these two probabilities by, dividing them with the sum of these two probabilities individually, so in that case, you find that the probability that this new customer is being liberal, that will come out to be 0.9161. All right. So based on that, you make a decision. All right, that's how this new customer. So this example gives you an idea of how Bayesian classifier is going to be used and what kind of situations are there where this could be very easily used. All right. So in this case, as the question was asked, where did we get those probabilities? All right. So those probabilities, not the a priori probabilities, but the conditional probabilities, are to be estimated in actual situations through the data that you collect as your training data. All right. So you will be, for any given problem, you will be collecting data, and from that data, you will be estimating these conditional probabilities. All right. Now, when you collect data, the attributes might be discrete or binary, as we had them in the previous example, or the attributes might be continuous attributes. So depending upon the nature of the attribute, you will be doing the calculations, or you will be estimating the probabilities accordingly. So here is an example where you estimate these probabilities. So essentially here we have data from 6 persons labeled as introverts and from 7 persons labeled as outgoing. So the first table is a table showing you data from class 1, let us say, and that is the class of introvert persons. The second table is the table of outgoing persons or extrovert persons, or class 2. And in one case, we have 6 readings, and in another case, we have 7. All right. In general, when people apply Bayesian classifier, either they will assume that the actual a priori probabilities are known, or they will make an assumption that your training set percentage of different classes is a good reflection of their corresponding probabilities. All right. So in this case, we have 6 examples from class 1 and 7 from class 2. So you can say that class 2 is slightly higher than class 1 to occur a priori. All right. In general, you'll find people either using this or just assuming that their priori probabilities are all equal. All right. So that's up to you to make that decision. All right. So in this case, we have this data, and obviously all these features are the same. So if you look at these two tables, so you can calculate what is the probability of feature 1 being equal to 1, given that we are talking of somebody who is an introvert. So that will be 1 by 2, because if you look at the distribution of zeros and ones, that is what it is. All right. And similarly, you can see what is the probability of F1 equal to 1 when we are talking of somebody who is an extrovert. All right. So we can calculate those conditional probabilities. And once you have the conditional probabilities, you can plug them in and get the results as you want. All right. So that's really how this will be done. Okay. So that's what happens in the discrete case or binary case. All right. Here is another example which is pretty popular. You might come across this example on many blog sites or in books. All right. So in this case, basically, you are looking at out. You're trying to decide whether we should play or not. We should go out and do golfing or not. And basically, we have a set of training examples to help us make the decision. All right, you're trying to build a system that takes certain number of inputs and tells you whether you should go out and play or not. All right. So in this case, if you look at the outlook of the day, basically you have three possibilities. It could be sunny, overcast, or rainy. Then yes and no numbers are shown there. Similarly, if you look at the temperature, and let's call the temperature not the actual number, but hot, mild, or cool. All right. So basically, again, you have yes and no, how many times you went and played and not played. All right. Humidity, high or normal. Again, that. What are the conditions? Windy conditions. So basically, you have this set of data, and you have 14 observations, 9 plays and 5 no plays. All right. So basically, you have 14 readings or 14 vectors, and every vector is characterizing a particular situation given through these numbers. All right. So again, you can apply the Bayesian classifier here. To do that, first you need to calculate the conditional probabilities and then plug in the formula to get the result. All right. So if you look at the bottom box in the slide at the left-hand side, that's where the conditional probability calculations are being shown, as well as the posteriori probability calculations are being shown. All right. So you can see that this is a pretty straightforward approach that can be applied, and it is really very easy to apply if we're talking of discrete or binary figures. All right. Now, you will come across a term which is known as Laplace smoothing. And this term will appear frequently if you are doing any work related to text mining or text classification. The idea of Laplace smoothing is to modify the formula for calculating probabilities to avoid zero probabilities and division by zero. Especially what happens if you're building a text classifier and you collected a lot of training examples. You identified, threw away the stop words, let us say, and you picked up the keywords and you calculated the frequencies of those keywords, and you got their probabilities and all that, conditional probabilities. All right. And then you get an email message that you want to classify. It's possible that the message will have some words which may not be there in your dictionary, for which the probability may not be there because it didn't occur anywhere. All right. So what happens is that in those cases, you're talking of zero probabilities, and in the calculation, if you carry on somewhere, you'll be multiplying with zeros, and might be dividing by zero somewhere. All right. So what you want to do is you want to avoid those situations. You don't want to say that probability is zero. You might want to say that probability is really, really small, but it's not zero. All right. And if you can do that, then you can avoid all those situations. All right. So that is what is done by Laplace smoothing. So basically, if you look at the formula here, I give you two formulas. One is the conditional probability without smoothing. So that's the formula typically people will use. All right. So if you are trying to calculate what is the probability for word I to be present in a document that belongs to class J. That probability is the count of documents where the word I is present and those documents are from class J. So you take that count and you divide that count by the count of documents of class J, and that will give you that probability. All right. With the smoothing, what you do is you add 1 to the numerator and you add 2 to the denominator. By doing so, what happens is that you avoid making probabilities become 0. All right. So this is what we call as Laplace smoothing. All right. And this is highly advisable to use when you are working with text classification problems or even other problems where you are dealing with binary features. All right. So let's look at what difference does this Laplace smoothing make. All right. So here are 4 documents in our training set. Each document is characterized by 6 words, or you can call them as 6 features. And there are 2 classes. And the classes are whether the topic is China or not. So basically, you're trying to figure out whether this a particular document is about China or it's not about China. All right. So those are the 2 classes, about China and not about China. All right. So the 4 training examples that you have. So the first document has a word Chinese in it, and that word is present once. It has a word Beijing in it. Shanghai is not present. Macau is not present. Tokyo is not present. Japan is not present. All right. And then the final column is telling you the class label. All right. Because these are training examples. So somebody has looked at it and they're saying, okay, the first 3 documents are definitely about China. And the 4th document is not about China. All right. And now your system is given a document, number 5. And for that document, the binary features are China is 1, Beijing 0, Shanghai 0, Macau 0, Tokyo 1, Japan 1. So should document 5 be classified as about China or not about China? All right. So again, to do that, what we'll do is you will follow the Bayes rule without Laplace correction, and we calculate all those conditional probabilities. We have the a priori probability. We plug them in, and we will get the answer. All right. So that's how this will work. All right. So once you have those conditional probabilities, you can take the document 5, plug in those conditional probabilities, and get an answer. All right. So basically, you can see that based on the 2 numbers that you get, document 5 is classified as not being about China. All right. So it's not about China. All right. Now, yes, please. Go back. Yeah.
If the 2 probabilities are equal, it will be done by
Well, if the 2 probabilities are equal, randomly you can toss a coin and decide. Okay. Now, when you are working with words, see the previous Laplace example I showed you, Laplace smoothing, you can say that is good when you are working with binary features. All right. But in many text classification problems, you are working with words and you have a dictionary. All right. So basically, you have many possibilities for a word. All right. So in that case, if you say that the number of possibilities for a word, if you take word as a placeholder and you want to fill in some word, there are whatever is the number of possible words in your dictionary, those are the possibilities. All right. So let us say that your vocabulary size is capital V. All right. So in that case, the Laplacian smoothing formula is what is shown here. So in the numerator, you still add 1 to avoid 0, but in the denominator, you add plus V. In the previous example of Laplace smoothing formula, in the denominator, we were adding 2. That was meant for binary features. All right. Because a binary feature has only 2 possibilities, 0 or 1. All right. So that's why we were plugging in 2 in the denominator. All right. So this formula is known as multinomial naive Bayesian model, because you're looking at not 2 possibilities, but you're looking at multiple possibilities. All right. So in text classification, typically that is what you will be using. All right. So if we take the same example that we took earlier, but follow the multinomial formula or smoothing formula for probabilities, then the numbers will be different. So these are the numbers you will get. And once you plug in these numbers to calculate the posteriori probabilities for the 2 classes, in this case, it says that the document comes from about China. So the decision has reversed. That is, you get a different result. All right. The reason you are getting different result is because the way you are calculating the probabilities. All right. So I just wanted you to know that there is something called Laplace smoothing, and that is a useful thing to use when you are dealing with binary or word type features. All right. So now let's see what happens when you deal with continuous attributes. That is, we are not talking of 1, 0 or words, but we are talking of actual numbers. For example, temperature or weight or anything else. All right. So when you have to estimate these conditional probabilities for continuous features, you have 2 possibilities or 2 approaches. One is convert the continuous feature into a discrete feature. That is, you take the whole range of values and put them into 5 or 10 or 2 bins. And that way, your feature becomes a discrete feature, and then follow whatever we have done so far to do the calculation. All right. So that's a simple approach. But a better approach is to basically make use of some underlying distribution function to calculate those probabilities. So the underlying distribution function that typically people use will be normal distribution or the Gaussian distribution. So you say I have a feature called temperature, and the distribution of temperature values has a Gaussian distribution. All right. So what you can do is, then you can, if you know the Gaussian distribution, which means if you know the parameters of the Gaussian distribution, and since we are looking at each feature individually, so we are working with univariate Gaussian features. That means each univariate Gaussian distribution can be described by finding out what is the mean value and what is the variance. All right. So once you know those 2 parameters, mean and variance or mean and standard deviation, then you know everything. So what you can do is you can then plug in the actual value you are observing and from there you can calculate what is the conditional probability. All right. So in practice for continuous features, typically what you will do is you will be making use of a Gaussian or a normal distribution. And we will be estimating these mean and variances from our training set. All right, so that's how typically this gets done. So here is an example. And if you go to the Moodle site, I think there is an Excel spreadsheet which basically shows you all the formulas that have been used here if you are interested in looking at those formulas. All right. What I'm going to show you here is simply the numbers and the results. All right. So basically we have a pair of observations. We are measuring temperature and we are measuring humidity. All right. And based on those two sets of values or measurements, based on our past record, we have an idea whether we played under those circumstances or we did not play under those circumstances. All right. So basically our class label is play, yes or no. And the two features are temperature and humidity. All right. So basically this is our training data. All right. So what we can do is we can actually now use the Gaussian distribution to calculate the probability. All right. So let us see that probability of not playing is 0.36, because if you divide the third column play, no and yes, you will find that 36% of the data says no, 64% of the data says yes. So we have taken those numbers as our prior probability. All right, so we have 0.36 and 0.6. All right. Now we take the mean value of temperature when we are talking of category no. So if you just take all the readings that belong to label no and calculate the mean of temperature, that turns out to be 74.6. Similar mean value for the other category is 73. If you calculate the standard deviation for temperature for the first category no, that is 8.81, and for the second category it is 6.16. Similarly, you do the calculations for humidity. All right. So basically what we have done is we have done the calculations for temperature and humidity conditioned on both the classes, play and do not play. And we have gotten the mean and the standard deviation. So once we have those numbers, and if somebody says, you know, the temperature is 78 and humidity is 82, should we go and play or not? So what we can do is we can plug in these numbers in our base formula and get the posteriori probability. All right. So if we plug in these numbers, ultimately the number that is highlighted in the yellow box basically is a higher number, and that corresponds to play. All right. So we say, all right, we go and play. All right. Now, if you want to see the underlying formulas, as I said, you go to the Moodle site, and I think the Excel worksheet is there, which you can click and see the actual formula. All right. So one thing is clear: you don't need anything other than Excel sheet to do Naive Bayesian classifier. All right. Now what we'll do is we'll look at a very interesting example for Naive Bayesian very quickly through this website or through this blog post. All right. So the basic problem here that is being described, actually I will leave it for you to go and browse through it and read it. Okay. But let me explain what is being done there. All right. And if you read this post, this basically covers the whole Naive Bayesian classification that we have discussed. All right. So basically, what we are saying here is everybody is familiar with 7-segment display, the kind of digits you see on your microwave and other digital device. All right. So suppose your digital display device has become faulty. So the digits are not being displayed correctly. So if you look at this slide here, in the blue is what you are seeing on your display. Now you want to predict, getting rid of the noise, what is the actual or the correct digit that should have been displayed. All right. Of course, in order to do that, you have to know what was the noisy version and what was the actual digit that was meant to be displayed. All right. So in a real life setting, that may not be possible. But what in this blog post we are doing is that we are taking these 10 digits to be displayed. So we have the correct pattern for each digit, which is nothing but a 7-dimensional vector of zeros and ones. And then we are adding some noise. So we know what is the correct digit that should be displayed. And we add some noise, and that gives us a noisy display. All right. So basically in this blog post, you will find we generate training data through simulation by starting with the correct digit, adding noise and seeing what pattern we get. All right. So we collect a lot of training data. And once the training data has been collected, we basically perform the calculations for conditional probabilities for the 7 segments conditioned on digit 0, 1, 2, and so on and so on. All right. So once you have all those conditional probabilities, then when you see a digit which is being displayed, which is noisy, you can then figure out by plugging in the Bayesian classifier what should be the correct digit or what was the correct digit that was meant to be displayed. All right. So basically, this blog post takes you through all these steps of designing a Bayesian classifier, generating data through simulation, calculating conditional probabilities, working with the test data, doing the classification. All right. So I strongly recommend that you take a look at that and go over that. All right. So let us summarize a Bayesian classifier. These are simple, easy to understand, build and implement, fast training and classification. Linear classifier, the result is a classifier which is linear, widely used in text mining and other applications. And these classifiers are kind of robust to isolated noisy points. They can handle missing features, because if a particular feature is missing, all you do is in your calculations, you basically omit that particular conditional probability for all the classes and calculate the rest of the, and do the rest of the calculation. So easy to handle missing features. It turns out that Naive Bayesian is reasonably robust to irrelevant attributes. For example, if an attribute has more or less 50-50 distribution for 2 classes, then that attribute is really not relevant because it doesn't really make any difference to your probability calculation. So it can be. All right. And as I said, the independence assumption may not hold in practice and generally doesn't hold in practice. But by making it, the error that you incur is really insignificant. So people really don't care. All right. But just to mention that, okay, if you were not to make that assumption, if you assume that all features do have a correlation, all right, and let us say that we are talking of continuous features, all right. So in that case, if you go back to our temperature and humidity example and say that the features are correlated, what you will be doing is you will be calculating the covariance matrix using that data. And with that covariance matrix, you will be fitting a bivariate Gaussian distribution. And then you will be using that bivariate Gaussian distribution in your Bayes formula. And it turns out that depending upon what kind of correlation matrix or covariance matrix you end up with, your resulting boundary might be still linear or it might be a quadratic boundary. So such classifiers are typically known as Gaussian classifiers because you are making full use of multi-dimensional Gaussian distribution. All right. So we will stop here for a minute or two because I need to switch to the next topic. All right. So if you want to step up and stand up and take a walk for 5 minutes, that's fine, no problem. Okay, so let's. Oh, okay, yeah.